I hope everyone's winter break was good, New Year's. I know that I am at this point pretty antsy and excited to be back in the swing of the spring semester. So I hope no one is dreading it too much. This is week 4 of GDSC Foundation Exam Review. The goal this week is to cover all of like the really mathy stuff. So summations, algorithm analysis, recurrence relations, space conversions. And then next week, we're planning to run a mock exam and go over answers to the questions, answer any other questions you guys have before the first foundation exam of 2023 happens. And that'll be not this coming Saturday, but the Saturday after. So hopefully most of you guys are registered for that. At the very end today, I think we're going to open up the floor for maybe 5 minutes before we all leave, just to see what you guys think would be the best format for running a mock exam. But we'll leave that for the very end when we have time. All right. Let me just make sure none of this is super important. All right, great. So we're going to jump into things today. And we're going to start with summations, just to make this clear. So I'm going to go ahead and start over here. And in order to talk about this, I think this is both, but we'll get back to that later. I want to first bring you guys over to the formula sheet. So if you go to UCF Foundations exam formula sheet, reference sheet, I can scroll down here all the way to the bottom, and we have a couple of summation formulas that are going to be really, really important for solving these summation problems. So I'm going to go ahead. What have I done? Opened YouTube Music. How have I done that? All right, I'm going to go ahead and copy these out, and I'm going to put them in a Word document where we're going to do all of our summation math. And then also, I'm going to grab one more formula that they did not include here, but I think is really important. Everyone should have, they'll give you a formula sheet on here, so you don't need to memorize those. I'm trying to remember what it was.
I remember it, if you want to write it down.
I was looking for the one where it's
the x
exponent.
Yeah, x to the I. I can write it down.
Okay.
So it's x to the I plus 1, and then there's a -1 on the outside of the exponent, and then you divide all that over x minus 1.
Okay, so it's i's from 1 to n. Oh no, it's from 0 to n. And then this is of
x to the I.
X to the I, right? It's equal to.
And it was x to the I plus 1. And then there's a -1 on the outside of that exponent. Yeah, and then it's just divided by x minus 1.
Oop. All right, this looks good to you. It would be -1. Okay, so this is the last formula here that does actually come up. There are a couple of problems that I came across that do have this formula. But essentially what we're going to do for all of these summation problems that we're going to come across, and honestly, I don't even really want to talk too much just about like how to do it in advance. We're just going to jump straight into some of the questions because I think it's easiest to understand how to do a summation just going through a couple of times in practice. But what you'll be given on these foundation exam questions is you'll either be given some combination of summations, maybe a summation of another summation, or some complicated summation formula. And you're going to be asked to turn it into closed form, which means make it an algebraic expression. There's no summations in there. It's all in terms of one variable, which is usually going to be n. And so, it'll be some really complicated expression. We need to simplify our summations using these formulas in order to get down to our closed form. You may not be given the summations directly. You may have a problem where it gives you a couple of lines of code. Maybe it's a couple of nested loops. And based on those nested loops, you need to write out the summations that represent that. And we'll do one or two problems like that because those can be a little bit tricky. But at each step, we just want to take our current summation, whatever our equation is, and use these formulas in order to simplify it. A couple of important rules that we can follow here. The first rule is that if we have a constant inside of our summation that's multiplied by something else, we can take our constant out and put it multiplied in front of our summation. And the other really important thing we can do is if we have any addition or subtraction inside of our summation, we can split it up into separate summations. So just to demonstrate that really quick, I'm going to use the word equation editor here. If you don't have familiarity with this, you will by the time you take discrete. But we can go ahead and represent summations in here pretty easily. What did I do this time?
Oh, by the way, Eli, it was x to the n plus 1, not I minus 1, I plus 1, my bad.
You're right. All right, good to know. All right, so we have our summation here, and let's say this goes I from 1 to n arbitrarily. And if we have, 5 times I squared here, well, we have our constant 5, and so we can go ahead and take that out, and the next time we write our summation here, this becomes 5 times /sum I equals 1 through n. And this is just I squared inside. And so now this summation matches our formula up here where we go from 1 to n, I squared, and it becomes this closed form solution. So what we want to do is we want to try and simplify it so we have something that matches one of these formulas and then replace it and then go ahead and simplify from there.
They're asking if you can zoom in, by the way.
Yes, I can definitely zoom in, and I guess I don't need to make it half the screen either. So this works. Another thing we can do here is if we had the same summation, but instead maybe it was 5 plus I squared, then instead what we can do is we can break this into two separate summations. One where we have 5 on the inside. And then one where we keep our I squared on the inside, and then we just add them together. We can solve these independently. There's an implied parentheses here. If you want to write your parentheses just to make sure that you don't confuse anything, it would probably be a good idea. You can't really afford to make too many mistakes that you have to go back through and redo your work because you don't have infinite amount of time. So anything you can do to keep yourself more organized would be recommended. So in this case, we can go ahead and solve our thing here. A summation of a constant is just this thing added however many times we're running of our summation. And so this would become 5n here, where we're summing 5n times from 1 to n. And then I squared would go ahead and replace with this nasty thing. And then we can add them together and make them more simplified. All right, so this is generally what we're going to do here. We're going to take all these rules and we're going to go ahead and solve a couple of summation problems. Let me just make sure everyone's good here, making it bigger. Great. All right, so let us go ahead and pick a new problem because this one talks about recurrence relations and we're not interested in that yet. All right, this is a quintessential summation problem. So it's not going to give us the sum, but we need to go ahead and figure it out based on this code here. So you have a code segment. We assume that n has been declared. It's just an arbitrary integer. And we need to write a summation, which is 3 nested sums. It tells us we have to have 3 nested sums. You could write this as 2 sums and then a constant on the inside if you go ahead and recognize what this code inside here does. But it wants us to go ahead and do it as 3 separate summations. So we need to make sure that we do that. And then after that, we're gonna go ahead and solve it and put it into closed form. All right, so let's go ahead and jump back into our word equation editor here. Hold on, I gotta screenshot this first just so we know what we're working with. And then here we go. All right, so problem number one, we have this code segment and A writes the three nested sums and then B turned into closed form. So let's go ahead and get started with part A here. So if we have a loop, essentially what we're saying is we're gonna run this loop n times, and then we're gonna run this inner loop based on whatever the current value of I is. And what this should tell you is that the inside of your summation index here, which normally runs from I equals 1 to n, is going to be generally based on the four conditions here. So this one runs starting at 1 and goes up until and including n. This one starts at 1 and goes up into and including I, which I is only defined inside the summation that represents this for loop. So we know that this one has to be nested inside. If it were outside, then I wouldn't be defined, it wouldn't make sense. And then we're gonna have a third summation that represents this in here. All right, so with this being said, let's go ahead and write our first summation. So let's write a summation to represent the outer loop here. And we're going to use the exact same index for obvious reasons. So we're going to use it as I. And this one is pretty easy. I is going to go from 1 to n. It literally tells us it starts at 1, it goes up until and including n, and it increments by 1 every time. Sometimes these will say that it's adding 2. Maybe it'll be divided by 2. You definitely want to look at what this post condition is here. If it's just an increment, then we do our normal summation. But if it's divided by 2, then essentially what we're doing is we're running it in terms of a logarithm. I'll see if we can find one of those just so we can practice. But this might be divided by 2, this might be plus equal to 2. Definitely make sure you're checking your post condition. But because it increments by 1 every time, we're safe here. And inside here, we need to put something else. And the very next thing that happens is we have another for loop, which is represented by another summation. So let's go ahead and write another summation here. And this one has a different condition. K starts at 1, but K goes up until and including I. So as I changes, K is going to go a different amount. So we're going to go ahead and write it up until and including I. And then this problem told us that we needed 3 nested sums. This part in here essentially just runs K times. It sets a variable equal to K, and then it subtracts away until it gets to 1. Once it goes below 1, then it doesn't run again. So this runs from 1 to K. And we could just go ahead and put we could put a K in here. That's what it simplifies to. But because it wants 3 nested sums, we're going to go ahead and write out that summation anyway. So this one, the variable is J, and J goes from 1. Well, technically J goes from K to 1 backwards, but we're just going to go ahead and flip this around. And then each time it performs how many operations? It performs 1 operation. It's going to decrement each time, and that is exactly 1 operation. So we have a constant 1 in here. And this is our 3 nested sums. Let me go ahead and make sure we all right, there we go. Got to fix the parentheses. My OCD would kill me otherwise. All right, so here we go. So we have 3 nested sums. What we're going to do is we're going to simplify them just one at a time. The easiest thing, the only thing that we can really do at this point is we can simplify this inside sum. So let's look down here at what our summation formulas tell us we can do. If we are summing a constant, we can take the constant outside, which doesn't help us. But essentially, this is just saying we're going to add 1 K times. And so this whole inside thing here just goes to k, which makes things much easier. And that makes things pretty easy. Let me actually go put this down here in section B, which is where this is. A just wants the closed form. All right, so we went ahead and solved our outer sum here. So now we have another summation over here. So let's go ahead and see what our formula tells we could do now. This summation is I goes from 1 to n of I. I in this case is represented by k, and then our n is represented by I. It doesn't actually matter what this is. You could have like 2n in here. You could have some algebraic expression. All of it just gets replaced by n in the formula. As long as the summation index has a multiplicity of 1 on the inside, we can go ahead and use this. So let's take this out, and this becomes, if we're saying that I is n, then I plus 1 divided by 2. That's what this becomes. All right, so we have another formula in here, but as this states, we do not have any easy formula that just tells us how to solve this. So what we need to do here is we need to go ahead and break this apart a little bit. So as we were saying earlier, if something is added together, we can split it into separate sums. First, we should just multiply everything out here. I'm going to go ahead and take the 2 out and make it a 1/2 in front. Since this is a constant divided by 2, we're going to go ahead and multiply it out front. Sum I equals 1 to n. And this becomes I squared plus I. All right, so we went ahead and split this up a little bit. We need to keep working on this. 1 divided by 2. And then we're going to split this into 2 separate summations now. And I'm going to go ahead and copy this for simplicity. So our first summation here, come on. We can keep as I squared. And then our second summation, is just going to be of I. And all of this is going to be multiplied by negative 1/2 in the end. All right. So if we're going to split our sums, our summation index stays the same, the range stays the same. We're just taking each side of the addition or subtraction and splitting it into a separate sum. All right, so with that, come on. We can go ahead and solve each part. So our I squared here, we have a formula that helps us with this. And so our I squared formula says that we have n plus 1 to n plus 1 divided by 6. This all works. And then our formula for summing I tells us that we have n plus 1 divided by 2. All right, so this is pretty nasty. You could, I think, turn this in and get full credit. They generally don't want you to like simplify it all the way down, but my OCD says that we're going to do that. So let's go ahead and break this apart. So let's multiply everything on the inside. So we'll keep our 1/2 out here for now. This becomes parentheses around this. N squared. We're just going to do it all together. So multiplying the left side, if we factor all of that, we're going to get 2n cubed plus n squared plus 2n squared plus n. And this is all going to be divided by 6. And then we're also going to have n squared plus n divided by 2. All right, let me just make sure this is all correct. 2n cubed, n squared, 2n squared plus n. Okay, this looks good to me. And so we can go ahead and next step, we'll go ahead and put our 1/2 on the inside. So we can multiply everything out. So now we have 2n cubed plus n squared. Let's go ahead and just make this 3n squared here plus n divided by 12 plus n squared plus n divided by 4. And I'm going to go ahead and multiply everything on the right side by 3 so that we have our common denominator of 12. And then let's go ahead and combine everything together. So we still have 2n cubed plus 6n squared plus 4n. And this is all going to be divided by 12. And if we simplify this one more time, we can split this up and we'll have n cubed divided by 6 plus n squared divided by 2 plus n divided by 3. All right. This looks to be our final closed form of our summation. We just have an algebraic expression. It's in terms of n. We'll go ahead and look at the ruling exactly, but you should be able to just turn in this. As long as you have done your summations correctly and everything is in terms of n, you don't have to simplify it all the way. But let's go ahead and check to make sure that this looks correct. So they went and kept it a little bit more closed. If we multiply this out, this is n cubed divided by 6, which is what we have. And then 2n squared plus n squared, which should be 3n squared divided by 6. So that's n squared divided by 2. And then n, so it'd be 2n divided by 6, so n divided by 3. Okay, so this simplifies to what we have here, which means that we are correct. And once again, they accept the factored form all the way up here or your polynomial down at the bottom. All right, that is problem number 1. Let's go ahead and jump into another summation problem unless there are any questions about how we did something here. All right, if you have any questions that pop up, feel free to unmute. We have plenty of time. I believe so. It didn't give us any criteria of where to stop. I don't think you have to simplify it all the way. I think you should be good just to leave it as soon as it everything's in terms of n. All right, so this is an interesting one. It gives us some variables here rather than entirely constants. B goes from A to A. 4B. All right, let's go ahead and see if we can decipher this one. Go ahead and take another screenshot and we'll put it in our Word document. All right, so we want a simplified closed form. If it asks for the simplified closed form, then you need to take it all the way down so that everything is as simplified as possible. So it wants a simplified closed form here. All right, so let's go ahead and build this in our equation editor. A is equal to 0 through n. B is equal to A through A of 4B. All right, so first step to solving any of our summation problems is we need to simplify our inside thing here. So we can go ahead and take our constant out if we want to. But let's pick up on the fact that we are going from A up until and including A, which means this only runs once, the summation only runs once with whatever the current value of A is in place of B. So my thought here is that we can literally just replace the summation pretty easily with 4A. Because this summation is going to run once, the value of B is A, and then it's going to add 4A to 0. So this summation gets simplified pretty easily here. Here's an important point to remember for summations. This summation that it gives us runs from 0 to n, but all of our formulas down here, barring 1, go from 1 to n. So this is a really important thing to keep in mind. If your formula tells you that you go from 1 to n, you can't just use the formula if it starts at 0. We need to go ahead and adjust our summation so that it starts at 1. And the way we can do this is we can go ahead and take the case of where A is 0 and just add it out in front. So when A is 0 here, we're adding 4 times 0, which is 0. So this doesn't actually affect anything. We're essentially saying we can adjust this. Actually, hold on. Let me make this a separate line here. We can say we're going to take out the case of A0 and add it out in front, but that case is literally just 4 times 0. And then we go ahead and add everything else, because this is what the definition of a summation is. We're just adding all of these different indexes together. We're just taking one out and adding it separately. So now that we have this, this becomes nothing. But now we do actually have a formula we can use. We have the summation of just I down here. But in this case, I is replaced by A. And we go from 1 to n of A. So in our next line here, this in front gets taken out. I'm going to take the 4 and put it in front since it's just a constant. And then we go ahead and use our summation formula here. A of A plus 1 divided by 2. And this simplifies pretty easily. This becomes 2A squared plus 2A. All right, this is our simplified closed form here. There's nothing else we can do to this make it simpler. And let's go ahead and check it. All right, and it gives us this thing here. Great. So polynomial form also accepted, which is what we gave. I like, to be honest, the grading on these really confuses me about how far they really want you to go. If it asks for simplified, I would take it all the way to polynomial form. For A. So if I is equal to 1, to begin with. So in this case, on this step, if we just started at 1 here, Omar. Yeah, so if it's 1 here, essentially we don't need to take out this step here where A starts at 0. Because A starts at 0, we have to change our summation bound, our range, so that it goes from 1 to something. And again, this could be like 2n, this could be n, squared, this could be literally anything. And in our, when we, put it in here, we just replace whatever this is with n. So if this were from 0 to 2n, we would take out the case of where A is 0. And then this is 2n, and then here, every time we have n, this would be 2a. Sorry. Oh, this should all be an n. I'm an idiot. I'm really smart. So this would be 2n here, and this would be 2n here. And then this would be here. All right, if you put it in terms of a, you're probably getting points off, so don't do that. All right, so that's what would happen if we had different bounds here. If it just started at 1 to 2n, then we just like don't have to take out this 0 case here. And it ends up being the exact same summation because in the end, you know, the 0 case here doesn't mean anything. If we had something on the inside, like maybe if we had 3 to the I, then our 0 case does matter because 3 to the 0th power is 1. And so we would take out here 1 plus, and then add the rest of our summation. That's when it would matter. If it's 0, then it doesn't matter as much. How did we get 4a? So we start here with our summation 4b. And we don't have any good formula down here that tells us how to solve this because everything starts at 1 and goes up through another constant. But the key, like, some of these summation problems are literally just plug in the formulas, but some of them will require you to like recognize something. You know, for up here, it's recognizing what the code does and where our bounds start and end when we're constructing our sums. Here, the key recognition is that this summation, the range is from a up and until and including a. So b goes from a up until and including a. So the only time this summation, you know, runs, or the only thing that's added here is the case of where b is equal to a. And then we go ahead and plug it in here for a, and then that's our whole summation. So the sum b is equal to a through a, or b is equal to 0 plus 4b, assuming that we're starting at 0, or 4a rather, and then this just becomes 4a. Our summation range always, the bottom is where it starts and the top is where it ends inclusive, because they are the same thing. It only runs the one time and the value that we're plugging in is a. And so it just becomes 4a here. If the top were less than b, then it wouldn't be a valid summation. We can't, you know, sum downwards. This has to be greater than this. Any other questions here? Lots of good summation problems. Definitely would recommend doing a couple, especially the ones with code, just so you can practice turning them into the summations. Even if you feel comfortable with actually solving the summation, sometimes like turning these, figuring out based on what the post condition is or where it stops or which index is based on another index can make these summations that you're building a little bit tricky. So definitely do a couple problems of those to review. All right, I'll pass it over to Zane so that we can actually get done hopefully on time.
All right, how's it going, everyone? Give me 1 second. All right, so we're gonna start off with recurrence relations. So typically, recurrence relations and summations, probably summations more. I'm not sure, but most people tend to have the most trouble across the whole exam with these two sections. So yeah, I hope I can help you guys out, especially with the recurrence relation. I'm also gonna do some other stuff later on, but all right, let's hop into it. So we have this is what most of the problems look like. They end up giving you some sort of statement where they tell you what type of work you have to do. So 3 iterations, and then you have to know the general form, do the iterations, and then, you know, get to some sort of answer with this. Like maybe right here, the big O runtime. Some of them, they're closed form, so you know you're just gonna have to put it like in terms of n. You can kind of remove certain constants and that sort of thing, but in this case it's just big O, so we can remove constants, and yeah. So we have this right here, so let's just write it down. 4t n divided by 2 plus 1. And then another important thing is also the base case. So t of 1 equals 1. So we have t of 1 equals 1. And this is going to be important after we get the general form. Okay, so when it comes to solving these, there's different ways of doing it. If you guys have, depending on the teacher you have, there's like master theorem and all that sort of stuff. But these questions are actually a lot simpler than they actually look. If you just notice certain things and keep track of how certain variables or numbers are changing. So first of all, we're going to want to do our 3 iterations. So what does that look like? We're going to want to think of it kind of how a recursive call works. So if this is a function t of n and we're calling another function t, the same function t, but a call within it, but to a different term, we know that this value is going to be changing, or really the value inside of here, but the way that it's going to run is going to be identical, which is why we can actually use substitution right here. So how's that going to look? 4 times. So this is, you can think of this like the first call you're making in a recursive call, because that's what
Can
it kind
I,
of, yeah.
sorry, just to interject, I think someone's mentioning that it should be plus n at the end of the formula rather than plus 1, which will
Oh, is
cause
it?
some
Okay,
issues.
my bad. All right, thank you. So yeah, you can think of this kind of like the first call, and then the next call is going to be very similar or really identical. So we're going to have 4t of, but now if we think about it, if we've divided by 2 already, and now we're going to maybe do another call on a number that's kind of being divided by 2 constantly, now we're not going to be at divided by 2, we're going to be at divided by 4. So this right here, I'm substituting what this call is going to look like once we end up, if we think about calling that function. So now we're also going to have a plus n. But the thing is right here, since your n is changing constantly, you're actually going to want to divide this term by 2. So this term was already divided by 2, but now we're going to divide again by 2, which makes it n divided by 4. This term was just n. And since we're dividing by 2, that means in the next call, our like quote unquote n is now going to be n divided by 2, and so on. So this is what the substitution is going to look like. And of course, we have to remember outside of the substitution, we have another term. So that's where we have our plus n. Okay, so now we can just go through it and keep solving. And we got to distribute. So let's distribute over. So we have 4 divided by 2. So we're just going to end up with a 2n plus the n we have at the end. And they want us to do 3 iterations. So when they say iterations, technically this first one is an iteration, and this is the second one right here. So let's just do it one more time. So it's going to look like 16 times. And again, it's going to look almost identical, except for the factors that are changing. So n is what's really changing, or like the variables. So 4 times t of n, not divided by 4. Notice that we're dividing by 2. So if we divide 2 and then we go and again, we're kind of like multiplying. So now it's going to be divided by 8. Okay. And now from here, we're going to have n divided by 4. And we still have our 2n plus n over here. So at this point, we're going to just distribute again. Plus, and then we have 16 over 4 times n. So again, that's going to be just 4. And now this is part of what comes with developing the answer that you're going to have for your general form and then ultimately for your big O. So we can notice 3 things. Whenever we do each iteration, of course, these are the iterations right here. And this one as well. We notice that there's a couple things changing, right? So first things first, we notice that these variables, so whatever's in the t function, whatever we're passing in, that's constantly changing. We're dividing it by what factor, like, or really like multiplying the denominator. So we notice that it's going 2, then times 2 in the next call, then in the next call, it's going to be times 3. So we can think of it like, okay, there's some factor that it's kind of getting exponentiated to, because if you think about it, like, yeah, 2 times 2 is really just 2 to the 2. 2 to the 2, or 2 times 2 times 2 is equal to 2 to the 3. So that's constantly getting bigger and bigger, right? And then we also have these terms right here, where they're going, okay, 4, then 16, then 64. So let's just think of this, in terms of, we can think of it in terms of 4. We can think of it in terms of 2. I'm going to put it in terms of 2 because if you notice, we have this term right here, which starts off at just a flat 2. So I'm just going to start off at 2. So we can think of 4 as 2 to the 2. Now, when it comes to this term right here, 16, we can think of this as 2 to the 4, right? And on the last iteration, we can think of this as 2 to the 6, because that's what 64 is. Okay, so again, we've just identified this is getting divided by 2 constantly. And right here, these values are growing. If we notice, it starts off at 2 to the 2, but then it's just going up by some sort of variable. And of course, 2 to the 1, or 2 times 1 is equal to 2. 2 times 2 is equal to 4. 2 times 3 is equal to 6. So now you can kind of see how the trend is building. So let's just think of this as 2 times 2. Think of this as just 2. And let's think of this, or 2 to the 1. 2 times 1, and then 2 times 3. Okay, so that part is important. Now let's also notice, again, like I had mentioned here, we can put this also in terms of 2 to the power of something. So this is 2 to the power of 3. This is 2 to the power of 2. And then we have 2 right here, which of course is 2 to the power of 1. So it goes 1, 2, and 3. Here we notice it's 2 times 1, 2 times 2, 2 times 3. So that's another clue, right? So we can think of maybe our k, which is usually what you're looking for. Maybe our k is 3 in this function, right? Or in this call right here. So maybe our k is 3. But let's just make sure with another piece of evidence, right? So notice here how we have, in the call that we're in right now, we ended up getting a 4, which is 2 to the 2, and then we multiply that times n, right? Then we have plus 2 to the 1 times n, and plus, how can we just get an n on its own? Is just 2 to the 0 times n. So we notice how, just kind of think of it like mirrored. So we start at 0, then we go 1, then we go 2. So you can say that this is kind of a summation, right? So this is a summation of terms. It starts from 0. And even if it didn't start from 0, you can do some math to figure it out. But it's starting from 0 and it's going up until 2, right? So far we have 0 and then 2. But let's just kind of think of it. Okay, if we're in the call of 64 times t of n over 8, how can we say, okay, the stopping point that we're at in this function right now, the place where we are, is 4n, which is 2 to the 2 times n. If you think about it, where can we get 2 from? We can just think of it as k minus 1, right? So this is 3 minus 1, which is equal to 2. And we can verify that, right? So we can look back and say, okay, so this is 2 to the 1. And let's see, actually, not right here. I meant right here. So this right here is 2 to the 1. And let's see, okay, our k here looks like it was 2. So 2 minus 1 equals 1. So the top bound of this function was also just k minus 1. And then for the summation in this one right here, it was just 2 to the 0, which also happens to be k minus 1. So our 0 right here is k minus 1. So we notice that in this summation that we're building throughout all these calls, it's really just adding up to it's just a summation, really. So let's kind of use that thought to see how we can end up coming up with a solution, right? So we know that this is likely, or it is 2 to the power of 2 to the k, because we're multiplying times k. Then we have, this is our general form, by the way. Then we have n divided by 2 to the k plus, and right here, this is a summation, right? So let's just think we're starting from 0, so I equals 0, and we're going up until k minus 1. And now what exactly is each term? It's just 2 to the power of something, right? The thing is, we're missing something. We're missing the n on the outside. Because if you just think about it, this is the same exact thing as this right here that we have. We just multiply it out. So this summation is just overall multiplied times n. And this is our general form right here. And now this is kind of where this value right here comes back into play. So t of 1, you're just going to take whatever is inside of the parentheses and set that equal to whatever's in the parentheses for this right here. So we have 1 equals n over 2 to the k. And that, we just multiply the denominator to the opposite side. So we're going to have 2 to the k equals n. And now we can end up substituting things to, solve for the answer. So let's think about it. Okay, so we know that right here, 2 to the k is equal to n. So if we substitute maybe n right here, or if we substitute instead 2 to the k right here, we're going to end up with just 1. And we know that t of 1 is equal to 1. So we can just remove that. So now we have t, or actually just times 1. Let me write this a little lower. Times t of 1, which we know it's going to end up being 1. So I'll just remove it right now. And we still have n. So this n right here, how can we end up, figuring out what this is, like what we're actually going to substitute for it? Because the thing is, we have what 2 to the k is equal to. So we know that that's equal to n. And normally in these types of problems, what you might end up doing is, substituting k, or sorry, substituting n or some sort of term right here. But the problem is, if we end up trying to solve for k, so we can substitute this right here, we're actually going to end up with log base 2 of n equals k, which, like, that's kind of you probably don't want to do that. It's probably possible, but you probably don't want to do that. So you can just leave it like this and think about it. Okay, how can I maybe transform this summation into something where I can substitute a 2 to the k, or maybe just plug in n at some point? So let's think about it. We have the summation formula. So again, this is the magic formula that you guys should write down. I don't know why they don't give it, but let's just write it down again. X to the I. Oh, actually, my bad. Let me remove this. N is equal to x to the n plus 1 minus 1 all over x minus 1. So this is a magic formula. And we can just substitute things in. So now we have 2 to the n plus 1, or sorry, 2 to the k minus 1. So remember, you're not using n, this is going to be your n. It's whatever's at the top bound. So k minus 1 plus 1. Then we have a minus 1 on the outside, and then we have 2 minus 1 at the denominator. And now right here, we're still left with 2 to the k, 2 times 2 to the k. Sorry, I said that wrong. 2 to the power of 2 to the k. You guys get what I'm saying. And then we have 2 to the k left over, minus 1. And you can just divide this by 1, but it's just 2 to the k minus 1. So right here is just 2 to the k minus 1. You can just end up distributing stuff out. So we have 2 to the k plus, And right here we have n times 2 to the k, and then minus, and this is where we're just going to have an n on the outside. Now from here, we have this term, but let's just think about how we can remove this too, because normally, it's not there, but it is. So how can we reproduce this term right here? We can just end up having, yeah, this right here. Or wait, yeah, we have a 4, so I think this, yeah, we can end up pulling this out. 6 to the k. Okay, or actually, my bad. Give me 1 second. I think I might have messed something up. Oh, actually, never mind, never mind. Okay, see what happened. So we still have, we're gonna have 2 to the k plus, and then we also have another 2 to the k right here. So what this is just gonna do is just gonna add the 2 k's. So we're, you can just think about it as k plus k, which is just ends up being 2 to the k. And then at this point, we still have these terms, but we can end up pulling out this 2 to the k. So now we have 2 to the k times 2 to the k plus n minus n, right? And now right here, you can just kind of substitute things out. So we can just have n's, we have n's everywhere. So this is just n times n plus n minus n, which ends up being n squared. Oh, really, we can just group these together, same thing. So 2n squared minus n, and this is our final solution. But the thing is, they want big O. So when they want big O, you're just gonna strip every single lower term and also every single constant to get your answer. So we know that n is really just n to the power of 1. And of course, n squared is greater than n to the power of 1. So we can just end up removing this term right here, right? So now we have 2 times n squared, and we can end up removing this constant right here, and that'll give us our big O. So our big O at the end of this is just n squared. So this is the solution. All right, so let's check that. Should be n squared. Yeah, so there we go. So I ended up going through the 3 iterations. And yeah, they have 4 right here, 4 to the power of k. But really just identifying it is just kind of like what Eli said. Even though there's usually summations in these recurrence relations problems, even in parts that aren't the summation, there's kind of like tricks or things you have to notice where the thing I like to say is like, it probably sounds crazy, but the numbers, they mean something. So whenever you see this 4 to the k, it means something. It's not just there just to be there. It's there for a reason. And if you kind of dissect it and twist it around, then you can get the answer from that. Yeah, they just don't end up adding these numbers for fun. So definitely just think of why is it there, because it's there for a reason. So let's go on to the next problem. So we have 2 times t of n divided by 4 plus 1. So this one's actually going to be very similar. Yeah, this one's going to be similar. This one's definitely going to be weird. It's going to be a little weird. So t of 1 equals 1. And then we have t of n equals 2 times t to the n divided by 4 plus 1. Now let me make sure this is correct. 2 times, yeah, this is correct. All right. So same process, 3 iterations, identify the pattern with the constants at every point. Okay, so really, the way I would kind of do it step by step, do the 3 iterations. After you've done the 3 iterations and it's nice and solved at every iteration, identify how these terms at the front are changing. So the constant to your t of n or your t of whatever it is, identify that, identify how this term is changing, or really how the overall term is changing. And then also identify what the summation is. It's going to be bounded by whatever k is. So once you identify those 3 parts, all it is algebra from that point, which might be the hard part, but yeah. So let's just go through it. So we make our substitution. We're just gonna multiply by 4. So we divide 4 and then we divide 4 again. We can just think about it divided by 16 plus 1. And then now here we're going to have a plus 1 on the outside. So now we're going to end up with 4 times n over 16 plus, when we distribute, we end up with a 2 and then a 1. So again, we see the summation building on the side. So let's go for another one. So now, instead of 16 times 4, now we're going to be at 64 plus 1. And remember, this is another part. People always forget these terms on the side, and it'll just make the problem pretty much unsolvable if you forget them and don't realize it. So plus 2 plus 1. And we're going to be left with 8 t of n over 64 plus 4 plus 2 plus 1. Okay, so that's our 3 iterations. So now let's go and see the trend. So this is 2 to the power of 1, right? This term right here is 2 to the power of 2. We can think of it like that. Now, yeah, and this term right here, let's just leave this one alone for now. Let's just focus on how these 2 numbers are changing. So next iteration, we end up seeing 2 to the power of 2. This is 2 to the power of 4. Okay. And in the last one, 2 to the power of 3. And this is 2 to the power of 6. Okay, so now we can kind of see what's going on. Let's just assume at this point our k is equal to 3, right? And this is where you can kind of check that it is by using this like summation that's building right here. So again, let's just sort it. So 1, 2, 4. Now you can see how the trend is kind of working. So we can think of this, as just 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0, right? So that's kind of what's going on. And you can represent this again as a summation. But what is it bounded by? What's the top bound? So we know we start at 0, right? So it's going to end at the top bound of 2. So how do we get 2? 3 minus 1. So now it looks very similar to the previous problem. But yeah, it's just they typically kind of follow the same type of pattern. Although this problem is going to give like a different answer than what you guys might expect. So now we can kind of think of our general form. So now we've kind of seen how the terms are changing. We know what it's going to be bounded by. Again, k minus 1. So now let's go for general form. So this is what our general form is going to be. So we have 2 to the k times t of n over. So let's just think about it real quick. So if we start off at 2 to the 2. We go 2 to the 4. And then we end up going 2 to the 6. And we know that k went 1, 2, 3. This can only mean that this is 2 to the power of 2 times k. Then we have a summation. We know it's bounded by the top of k minus 1. since it's, right here, 3 minus 1 is 2. And we start at 0 because that was the first term. The only way you can get a 1 if you're doing, exponents and that sort of stuff, unless it's just 1 or, a -1 or whatever, is just doing it to the power of 0. So you start off at 0. And now here we're going to have a 2 to the power of I. So this is our summation, right? So this is the general form that we have right now. And now from this one, we just got to kind of solve. So let's see what our base case was. So it's t of 1. So take what's inside of here, set it equal to this over here. So we're going to have n equals 2 to the power of 2 to the k, 2 times k. And now from this point, let's just think like, what term can we see is going to be or is in our general form that we can get from this? So of course, we don't have any 2 times 2 to the power of 2 times k. We don't have this anywhere. The closest thing we do have is this right here. Let's see what else we got. So, we also have one right here. So that's okay. But we're kind of solving it right now. So we can't really think of it like that right now. But we also have this right here. So let's just kind of see what term can we kind of come up with from the summation where we can get rid of it and also, get rid of this 2 to the k, right? And there's actually a way you can tell, but I'll show it a little bit later on. I'll just do it this way. So we know that we have our magic formula. Yeah. Nafal knows. Okay, so we have this magic formula, right? So let's use the magic formula. So we're going to have 2 to the power of, now our n is k minus 1, and we have our plus 1. Then we have the minus 1 on the outside, divide that all by 2 or 1, or 2 minus 1. So what's that going to leave us with? It's just going to leave us with, 2 minus 1 as the denominator. And then we can just remove this minus 1 plus 1. So now our term is going to be, let's erase real quick. Okay, that's not the erase. So it's going to be 2 to the k minus 1 is where we're going to be left over with. 2 to the k minus 1 is what we got. All right. And now at this point, and yeah, we can end up solving for this. We know that this is just going to end up, since they're equal to each other, we can substitute this as 1. So this is just like t of 1, which is just 1, and we're multiplying it. So we can remove it. So now we have these terms left over. So how can we solve this and remove this k finally? The thing is, you can actually end up taking the square root of both sides because, for example, let's say you have, this term right here. Whenever you have a 2 to the k or maybe a 2 to the n or whatever it is, what it really looks like, if you write it a little bit differently, is this right here. So this is the equivalent because, again, you do the math, and it's k plus k, which is just 2 to the k. So if we take the square root of that, which we know that this, we can kind of process it a little differently. We can also think of it like this. We can end up thinking of it like 2 to the power of 2 times k. Or you can think of it also in another light. You can think of it, which is kind of probably the easiest way to think of it. You can think of it as, because remember, whenever you have a power to on another power, then you just multiply. So you can actually think of it as 2 to the k to the power of 2. And these are all equal to each other. These things are all equal to each other right here. They're all the same thing. But if we end up kind of thinking about it like this one over here, the one on the right, let me just move this over. If we end up thinking about it like this, we can actually take the square root of both sides. Right? So let's just substitute. Since this is the same exact thing, let's just substitute. So we're going to have 2 to the k over 2. And if we take the square root of both sides, Okay, now we have a square root of n. I promise this is good. This is good. And now we can end up removing this. So we take the square root. Now you're just gonna have n squared equals 2 to the k. Now 2 to the k on its own, not 2 to the power of 2 times k or anything like that. This term is something we have and we know we can substitute for easily. So now it's just a matter of substituting things. So we're just gonna have this right here plus n squared again minus 1. And this is going to leave us with 2n squared minus 1. And our answer is just going to be, if they're asking for big O, it's just going to be big O. Let me write the O of the square root of n. My bad. I was saying n squared. I meant the square root of n. So this is the process for this one. But just notice, even though it was a different problem and you know, we kind of went through a little differently, the process is generally the same. Just end up finding the trend. And once you have the trend, you just have to do the algebra, which can be the trickiest part, like I mentioned. So yeah, let's check our answer. Okay, so here we go. So let's just see kind of what they ended up doing real quick. So yeah, they ended up at this point. And the thing is, I do want to say this and mention this. They don't really show you the jumps from this point to this point, and especially from this point to this point right here. Like I mean, you can kind of do the math, but they don't kind of show you, okay, like where does this term come out of? And it comes out of the formula that for some reason they barely give you. So it's the magic formula. This one right here. This is how they ended up doing that. So it's very important. Please write down that formula. I'm telling you, you guys, it's gonna come up. Yeah, so I can explain why I did that. So what I had mentioned was when we had this term right here. So this is our general form, and we always want to solve this by setting it equal to what's inside of the base case. So t of 1 equals 1, right? So we're going to set this term equal to what's inside of here. So that leaves us with, go through it again, n divided by this term equals 1. And we can just get them equal to each other by multiplying. So we end up with n equals this, right? So this is where we're at right now. Now, for us to get it into a way where we can substitute it, so we have this term. It looks very similar to what we have in our general form, 2 to the power of k. But the thing is, we can't actually substitute this in for this because, you know, it's just not the same term. So the thing is, we also want to figure out what else we can substitute for this right here, which it ends up simplifying out to 2 to the k. So now that we know that, we have 2 to the k and a 2 to the k. So we have to think, how can we go from what we have right here, n equals this term, how can we take this value to something that's 2 to the k, right? And the way we can do that is by using the square root, because, you know, there's like rules to the powers where these things are equivalent. So 2 to the k is equal to 2 to the 2 to the power of k. Whenever you have a power to a power, you just multiply it. So it's the same thing. But the thing is, you know, like you're not trying to take the kth root or whatever. You're trying to take the square root because that's the easiest, right? So if we know that by multiplying, it's the same exact thing, like we're still going to end up with, you know, this term, we can just end up switching k and 2. So now we're going to have 2 to the power of k. Okay, we've seen that before. And now we have a 2. So these three terms are the same. And if we end up square rooting, so if we just substitute this right in for this term right here, we're going to end up with 2 to the k squared. We take the square root of both sides, and now we have a term, and really, you know, just the key to the question, but it's really a term that we've seen before that's in our general form and we can use. So we can use it to substitute for this, and that gives us our answer. So that's why I ended up taking the square root. This is literally the only square root problem that'll come up. You know, they might do it on this next one, but don't be scared of it. It's not that bad. You just gotta identify. You just gotta be clever about, you know, how the numbers are structured. Okay, so I think I'm going to pass it off there. Eli, do you think I should do one more question? Or just hop into the next one?
I think we should keep moving just so we can try and get things, and if we have time at the end, we could do another recurrence
Okay,
relation
yeah,
question.
sure. So I'll pass it over to you then.
Alright, I'll go ahead and cover base conversion, which should be pretty quick. And then I don't know what you have in plans for the algorithm
Yeah.
analysis, so we'll see. Alright, let me go ahead and share my screen. Alright, here we go. So let's go ahead and look, because I know someone just put in the chat on the big Discord asking if base conversion was on the exam, and it is. You will have questions that ask you specifically to convert one number that's in some base to another base, which all of the ones that I've seen so far have been involving hexadecimal, octal, decimal, or binary. I haven't seen any that are anything else, but you should know how to do it. But those are the big ones. So just like a quick recap of what bases are, all of our numbers that we have are in base 10, which means that all of the digits of this number are in increasingly powers of 10. So this number can be expanded out as 3 times 10 to the third plus 4 times 10 to the second plus 6 times 10 to the first plus 3 times 10 to 0. And so this becomes 3 times 1000 plus 4 times 100 plus 6 times 10 plus 3. And then if we add all these together, we'll get our number here. And so we can say that this is in decimal, which is base 10. This is what we use. On a daily basis. All right. Other bases that are important to know, binary is base 2. You should all be familiar with that at this point, but everything is increasingly powers of 2. So our first place is the ones place, and then 2, and then 4, and 6. Sorry, not 6. 8, 16, 32, yada, yada, yada. We can have octal, which is base 8. So again, our first place is 8 to the 0, which is 1. Our second place is 8 to the first, which is 8. 8 squared is 64. I don't know what the next power is here. I want to say maybe 512. Yeah, I think this is 8 cubed. And then this hexadecimal is base 16. So our places are 1, 16, 256, 40, 96, so on and so forth. Okay, so we have this. We need to take a number and convert it from one base to another in order to do so. The one thing to note here, one thing to remember is that in any particular base, the only digits you can use are the numbers, the digits 0 up to and including that base. Sorry, up to but not including that base. So if we have decimal, which is base 10, we can use digits 1, 2, 3, 4, 5, 6, 7, 8, 9. But not including 10. If we have base 8, we can use 0, 1, 2, 3, 4, 5, 6, 7, but not 8. And if we do need to use an 8-digit in some place, then we need to go ahead and carry it into the next place instead. Binary is, of course, only ones and zeros because it's up and two, but not including two. Hexadecimal is the one that's a little bit more confusing because we run out of digits. We can go up until 9, but we don't have any digits that can represent 2-digit numbers. And so we go ahead and use letters after this, A through F. So A represents if we need 11 of whatever this place is, and then 10, 11, 12, 13, 14, and 15. Again, if we get to 16, we just need to use the next place value over. So there's nothing past F. Okay, so there's a couple things that we should note here. There are some tricks that we can use. One really cool trick, if we have, let's pick a random, hexadecimal number. If this is base 16, we can convert octal and hexadecimal into binary really easily, just by recognizing that essentially we take each digit here and represent them independently as binary and then just smudge it all together. So 3 represented in binary, and we're gonna, for hexadecimal, we're gonna have every digit represented by 4 binary digits. So 3 is represented by 0, 0, 1, 1. So this is a 1 in the ones place, a 1 in the twos place, and then 4 and 8 are zeros. So this is 3. And then our D translates to 10, 11, 12, 13. So we can represent 13 with an 8, a 1, no 2s, and a 1. And then we can represent 6 with no 8s, but a 4, a 2, and no 1s. And this is base 2. And so this is our hexadecimal number, very easily converted into binary just by taking each digit, giving it, exactly 4 binary digits, and then just smudging them all together. And we can do the same thing for an octal number. If we have 1, 5, 7 maybe, and this is in base 8, we can do it, but using only 3 digits this time for octal. So a 1 is 0, 0, 1. 5 would be 1, 0, 1, because again, we're representing it in binary. So this is the ones place, the twos place, the fours place. So this is 1 plus 4 is equal to 5. And then a 7 we represent as 4 plus 2 plus 1, base 2. So this is our binary number that represents it. We could go ahead and take the spaces out if we want to, but it's fine here. So this is a really easy way to convert from one to the other. We can also do this backwards. Like if we saw a binary number like this, we can split it into 4-digit sections or 3-digit sections and then quickly make a hexadecimal or an octal number out of it. It's also important to be able to convert from any base to decimal and then from decimal to any base. Like if you went from like base 7 to base 3, that can be really complicated. So we can use our hex or decimal and as like an intermediary. I personally would solve all of these problems the exact same way. I would, you do have to be able to recognize these tricks because I did see 1 or 2 questions as I was going through review that asked you to use one of these tricks. But for any question that you don't need a trick, you can go through the whole process if you don't feel comfortable. So let's say we had this number 3D16, and we want to convert this into base 7, let's say. Some number base 7. So what we can do here is we need to first convert this into decimal. And what I'm going to do is I'm going to list out all of our decimal places just so that we know what we have. So this would be 10, then we have 100, we have 1,000, yada, yada, yada. So let's say that our number here is 3D6. In order to figure out what this is in decimal, we can go ahead and just take the place that this represents and then multiply it out. Sorry, I should not have listed decimal here. We should list what each of these digits in hexadecimal represents. So our furthest right digit represents 16 to the 0, which is 1. And then 16 to the first is equal to 16. And then 16 squared is equal to 256. So this number, if we convert into hexadecimal, we just multiply whatever the value of the digit is times the place value. So this is 3 times 16 squared plus D represents 13. 10 is A, B is 11, C is 12, D is 13. 13 times 16 to the first plus 6 times 16 to the 0th. And if we add this all together, this is 256 times 3, so that's 750, 768 plus 13 times 16 would be 160 plus 48, so this would be 208, and then 6 times 16, 80, 96. We can add all these together. This would be 304, 172, 1072. All right, I think this works. Can someone check my math? 1072. Nope, I did it wrong. All right, 982 is what our math is here. Oh, you're right. I'm a genius. All right, thanks guys. All right, so this comes out to 982 and this is base 10. And now we can take our base 10 and convert it into anything we want. So let's list out our sevens places here. So 7 to the 0th is equal to 1. 7 to the first is equal to 7. 7 squared is equal to 49. Let's do 7 cubed. I don't think we'll need to go any higher than this. I don't actually know what this is. 343. All right, so this is what we have here. So we can recognize that 343 times 7 is going to be way bigger than our decimal, the number that we have here. So we won't need any other places beyond this over here. So we'll need exactly 4 digits to represent this in base 7. So let's figure out how many times 343 goes into 982. So 982 divided by 343, and my calculator says it goes in 2 times evenly. And then 2 times 343 is equal to 686. So 982 minus 686, and we'll go ahead and store our number down here. This goes in twice for the first digit. And this leaves us with 296. Yeah, 296. All right, so then we have 49. So how many times does 49 go into that? We could do 296 divided by 49. That goes in 6 times evenly. So our new digit down here is a 6. And 6 times 49 is 294. Minus 294 is equal to 2. So we have 2 left over. Can we do 7 into that? No. So this is a 0. And then this goes in twice here. All right. So this is our final number down here. This is in base 7. And these 3 are all equivalent. So this in hexadecimal, this in decimal, and this in base 7. This is a general process. We'll go through all of these problems. If you can't, do it easily with a trick, note that this only works from hexadecimal to binary or binary to hexadecimal, and same thing for octal to binary, binary to octal. Like this trick doesn't work for if you're converting into decimal or anything like that. So if you're allowed to do the trick for the problem, great. Otherwise, you'll have to go through the whole process. So the reason why D is 13 is because once we run out of digits, each letter starting from A is exactly one higher. So A represents 10 for any base that's 11 or higher that needs a 10 digit. So A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. And this makes sense because hexadecimal, we can't have a digit equal to 16. That would be overflowing. So we end at 15. All right, so that's how we solve all these problems. I'm going to do one of these really quick and then pass it off since they are pretty monotonous. We can do this one really quick. Convert the hexadecimal number AF2E9 into binary without, so note that this one says without converting to base 10 first, which means we have to use the trick. We're not allowed to do it the long way. AF2E9. And this is in base 16. So if we convert each of these into binary, they're individual binary representations. A is 11, so we have a 8 plus 4 plus 1, that equals, nope, 8 plus 2 plus 1, that equals 11. And then F is 15, which means everything is a 1. 2, we only put a 1 in the 2 digits. E represents 14, so we have an 8 plus 4, which is 12, plus 2, which is 14, plus 0. And then 9, we have an 8, no 4s, no 2s, and a 1. All right, and so this is our number, very easily converted into binary. And this is the first part of the question. We can go ahead and validate that it worked. The second problem is that it gives us some candles here. Unlit candle is a 0, a lit candle is a 1. How old is he based on the picture? So this is 1's place, 2 place, 4, 8, 16, 32. So this is 1 plus 2 plus 4, skip 8, skip 16 plus 32. So 32 plus 4 plus 2 plus 1 is equal to 39. So he should be 39 years old. Let's go ahead and submit this, make sure we got it. All right, so he is 39 years old here. And then let's make sure we have the right thing. Oh, what did I mess up? Oh, this should be 1010. This is 10, which means we have an 8 plus a 2. All right, these problems are pretty monotonous, to be honest. So I would definitely be aware of how to do this long process. You should be able to convert it to decimal and then decimal to anything else. It does come up pretty often. I had an interview question that asked me to write code to do this. So it is a useful skill, even if it's not necessarily on the foundation exam. But would definitely be aware. All right, I'm gonna pass it off to Zane, so you have half an hour to do the important stuff, which is algorithm analysis.
Okay. Give me 1 second. Okay, so let's do some algorithm analysis. Oh, fun. All right, let's do this one. So we're gonna start off. Okay, let me just remove this. This one is actually the type of problem that is, I think, for me personally, probably the easier ones to kind of look through and analyze versus some of the other ones where, maybe you have to write some sort of like proof or recurrence relation, write some sort of summation. But yeah, I actually enjoy these a lot more. So in these ones, you're just kind of looking at the code and seeing, okay, the runtime. So what's the time complexity of this code? So you're going to want to nitpick every single thing because it can throw off your answer. The smallest thing that may or may not look like it does much, it can, add an entire maybe square to your runtime or time complexity. So let's just look at this. So for each of the following functions in terms of n and or k, where k is the length of the string, given that string length is an O of k function and to upper is an O of 1 function. Okay, so pretty much they're just saying that string length runs in O of k. You can think of that like O of n, but you should use k because that's what they're asking you to use or referencing it as. And to upper is O of 1, so we don't really have to think much about that one. And you can assume that it's not null. So let's figure out what the runtime is for the first example. So it's a function, you're passing a string, just like all these other problems. And there's a for loop, right? So we can just think of it like this. So there's a for loop, and it's going to be based on whatever the length of the string is. Yeah, so it's based on whatever the length of the string is. So we know that for sure the length of the string is going to be k, right? So length of string equals to k. Okay, so we know that calling this is an O of k function. So as of right now, we're at O of k because we have to call this at least once to run, right? And since we're going to be iterating to up until k, which is the length of the string, we know at least we're going to be at O of k. But the thing is, you are going to be checking this condition at every single index of the string. So for example, if we have a word hello, you're going to have an index that's going to start at h. So right here, you're going to start off and say, okay, let's call string length. So that's O of k. So that's a k, right? Then you're going to do it again at e. Okay, let's check if this condition is true. Is index 1 less than the length of the string by calling string length, not saving a variable, by calling string length every time. So that's going to give you another k, and so on. So we're going to actually have not 5 Ks, because you also have the case of the break case. So now right here, we're going to have a 6th one. But you can think of that kind of as extra. It's just always going to be there. So based on, I wrote this wrong. Yeah, there we go. So we have 5 Ks and we have an extra one that's always going to be there. So we can just think of this as, okay, we're going to do a k operation for every single index of the string. And overall, the string has k letters. So we can just think of this as k squared at this point. You can think of this as, k squared. And if we add these all out, we're going to end up with a 5 plus k. And we know that the runtime overall of that is just O of k squared. So that's the idea. At every single index, you're making an O of k call. So there's k indexes, O of k call per index, so k squared. So that's the runtime on that one. Now in this one, they actually write it out a little differently. So the only thing that changes right here is they call string length outside of the for loop right before it. But instead of calling it right here on the condition every time, they use a variable that has saved that value beforehand. So now if we think about it, we're saving the value when we called string length once, right? So now in this case, again, we have O of k. So this is for problem 2. We have O of k. And then now we're going to do a for loop based on the length of that, but we're not calling string length repeatedly at every index. We know that there's k indexes, but we're not calling that. So we're just going to have a for loop through k elements again. So we can just think of this as 2k, which is just O of k again. And we know that 2 upper again is O of 1 function, O of 1 function. Now here, let's see what we have. So we have this actually, just comment what algorithm this kind of looks like. So we have I equals 0 and then j equals string length minus 1. And then we have an m variable and we have a while loop while I is less than or equal to j. Okay, so it actually, even though it looks very weird, this is actually similar to binary search. And you can kind of tell by how they set up the problem that there's an m, so mid, And the way they actually did this, it's the same thing as doing I plus j divided by 2. It's just the same exact thing. It just finds like the difference and divides by 2. So it does the same thing. So this calculates the mid. And what it does here is check, okay, if some random number that we come out from calling this, like let's say it's 3, if this number is even or if it's odd, do this and move towards this direction in the binary search. So randomly, we're going to move left or we're going to move right, just depending on whatever that number is that generates. So we can move left or right, not on any specific way, just randomly. So we're going to be cutting the space by half. So if we have a string of length 100, now in the next one, we're going to be looking at 50 elements. It might be on the left, it might be on the right. And same thing on the next call. Now we're going to be looking at 25. It might be on the left of that or on the right of that. It doesn't matter. So overall, we only call string length once. So we have O of k plus, and again, we also have another factor, but this here is going to be log of k. So that's going to be log of k, and yeah, it's just reassigning stuff. And I don't know if they want it to be just overall. Yeah, just big O. So let's just say O of k overall, because k is bigger than log of k. All right, so now we can go to the next one. And mad scramble. Okay. So we have a string, and this time it's a little different. We're not calling string length in the function. If this were written a little differently, that would matter, but we're passing the length, and we're doing a for loop based on that length that we're not calculating again, like string length. But the thing is, even though the condition is not being called by, like it's not bounded by like calling string length again and again, like this one up here, or sorry, this one up here, we're going to be iterating up until n. So we know for sure at minimum O of n or O of k. But the thing is, inside of every single, valid condition. So for example, if n is 5 and I starts at 0, for 0, 1, 2, 3, and 4, it's going to call string length of s. And we know that that again is an O of k function. So if we have a string of length n, which we can just kind of like equate to k, because k is again the length of the string, then we can think of this again as a k times k function, because for every index for a string of length k, we're calling a function that's O of k. So that's just k squared. So it's almost the same as the previous problem. The only difference is that this is going to be called, if the string is of length 5, this is going to be called 4 times. And then, or actually, sorry, it'll be called 5 times. Meanwhile, if you were to put a string length right here, it would be called 6 times because you have the break case. This doesn't run during any break cases. So that's the whole idea behind that one. So let's just say get a square on this one. And let's see what the answer is. Yeah, so we have k squared on the first one right here. O of k on the second one. This one right here, same thing. So string length plus, and we have the binary search, the log of k. And then we have, n times k. Okay, so they actually decided not to keep it as just k. They actually set it to n. I'm not sure like why they did that, because the thing is, you're only supposed to iterate up until n, and if you're going to be like indexing into the string, then or actually you're going to be changing, let's see.
Well, I think n and k are separate because n could be anything. Like it's not like they're passing in the length of the string.
Okay.
N is like a totally separate variable.
Okay. Yeah, for some reason I thought it was like I just kind of like equated it to
That's generally what you would do. Like you'd
yeah,
pass in the length of the string. So
yeah,
it's a valid conclusion to make.
right. So okay, so my bad on that one. It's just think of it as actually right here, n times k. All right, so yeah, they try to get you one of those. They just got me. So all right, let's do this one. So this is one of those math problems that tends to come up with these, and you got to be very careful on these. But typically, these should be free points for the most part. There's some that are trickier than others, but let's just write down what the terms are. So we have O of R C squared, and we know that our R of 200, our C of 500, and I'm gonna, go full screen on this in a second. This takes 5 seconds. And then we're gonna calculate R of 800, calculate C of 300, and we want to figure out what the amount of time is in seconds. So how long is the algorithm gonna take? So let's figure it out. All right, so first things first, we know that we have to set it up some way. So you can think of it like T of n equals C times. And by the way, this C, you can think of it as a constant. Don't think of it as this C. Like conveniently, it's the same letter, but just think of this as a constant. I'll just, for this problem only, I'll call this K for constant. And then we have our RC squared. So we're gonna want to plug all these terms in to kind of figure out what the constant is. So we have the time, we have the R, we have the C. The only variable that we're not going to know is going to be the K, the constant. And that way we can use that to solve this input for the time. So if the amount of time it took was 5 seconds, let's just set this equal to 5 right off the bat. Then we have K right here. And we have an R of 200 times a C of 500. 500 squared. Let's just put it in here. Okay, so the thing is, with these type of problems, I like to break it up and use as many powers of 10, because I think that's easier to calculate than these numbers. Like they're not that bad to calculate, but when you have like 64 million times, some other number, it's probably really hard to divide that or, multiply it out. So for example, we know that 200 is equal to 10 squared times 2. So that's how I like to think of it. And then we have 500 squared. So we can think of this as 5 squared times 10 squared. But the thing is, this is 25. So we're squaring the 5. And then we can think of it as, because we have 500. 500 is just 5 times 100, right? If we're squaring this, we're going to end up with 5 squared times 10 or 100 squared. But if we're putting in powers of 10, 100 is actually 10 squared. And if we square that, it becomes 10 to the 4. So now we're going to have times 10 to the 4. And you guys will see why it makes things easier in a bit. At least I think it is. So then 10 to the 6. So if we multiply these out, so this is all multiplication. We're just multiplying stuff out right here. So we have 10 squared times 10 to the 4. We just add them together. And now we're going to have 2 times 25, which is just 50. So K times 10 to the 6 times 50. You can pull out another 10, but we'll just leave it like this. So equals 5. That would actually make it it'll be about the same thing pretty much, but we can divide this term out on both sides to solve for it. So now we're going to have times 50. Let's just divide this times 50. And now we have this term divided by this. We can simplify it, but we just kind of have to think about how. So we have a 50, and we can think of it as, right, so 5 over 50, that'll give us 110. So we can just remove this 5 right here, and make this what our K is equal to. So now this is what our K is. So this is the term that we're working with. And if we have 10 to the 6 times 10 to the just 10 is 10 to the 1. We're actually working with this term right here. Okay, so that was a couple steps of kind of, moving the numbers around, but now let's go on to the other part of the problem. So that way we can kind of see why it's nice to do that way. So now we have the constant. We just have to figure out what the time is going to be based on, whatever inputs we're going to pass in. So we're going to pass in, what was it? It was R and C of 800 and then 300. So I'll just say N, or just really whatever we're going to be passing in. You can think of this actually as R and C, but it's going to be 800 and 300 and so on. So we have our constant. Let's plug that in, 10 to the 7. Now we have the terms. So we have 800. So this is our R times our C squared. So C squared is 300 squared. And now again, we can just change the numbers up. So we can think of this 800 as 8 times 10 squared. And we can think of this 300 squared actually as, let's break it down, 3 times 10 squared. And we can square this. So that's going to give us 3 squared, which is 9. And then we square this power, we'll just multiply the powers. So now we have 9 times 10 to the 4. Okay, so now at this point, we have this. So this is what we're working with right now. So now what we got to do is just combine terms again. So we have an 8 times 9, so that's 72, times, and then we can bring these two together since we're multiplying. So 10 to the 6. And now at this point, we have a 10, and we multiply this out. So now we have, it's over 10 to the 7. Now, right here, you can break it up a little further, but let's just leave it like this. And then I'll show how you can break it up. You can subtract these out. And the thing is, if this exponent, like it's the same base, and then, you're multiplying, if this exponent at the top is greater than the one at the bottom, it's just going to be, what do you call it? It's just going to be just divide, or sorry, you're going to be subtracting it out. So you're going to have 72 divided by this, and you're going to be left over with a 10 right here. And that's going to be 7.2 s. So this is our answer right here. Okay, so what I had mentioned with how you can kind of do it a little differently, 72, we can also think of this as 7.2 times 10 to the 1. And if we think of it like that, we can multiply this times 10 to the 6, and that'll leave us with 7.2 times 10 to the 7 over 10 to the 7, and that's it. 7.2 is your answer. So it's just a different way of looking at it and doing it. But yeah, 7.2 seconds should be our answer. Let's see. Okay, there we go. Yeah, so they ended up doing the same approach, but really just moving the numbers around to get it from, whatever the numbers are to, just easy powers of 10 multiplied to some number. It'll take a little bit of work, but it's not that bad. Oh, why did we divide by 10 to the 7? Yeah, I got you. So it's because that's the constant that we found. So we ended up doing all this stuff. So we were given the time, so 5 seconds right here. So we have this. Let's just do a check. So we have this right here. We have R, we have C. The only thing we don't have is K. So you have to solve for K, which is a constant. Once you solve for that, you have this equation right here, which, okay, we have the R, we have the C, we don't have the time, so we don't have the time. And the thing we have now is the K. So we're only looking for one variable, and before we were looking for K, but now we're actually looking for the time now that we have K. So yeah, it's just like solving for different variables and also for different inputs on the second case. All right, so let's go on to the next type of problem. Okay, so this is literally the same thing. So let's just go on to another one. Okay, this is one of the fun ones. Okay, so with proof, determine big O runtime of the function. So below, in terms of the input parameter n, you may use results from algorithms previously studied in COP 3502 CS1 without restating the full proof of runtime. So in this one, you get lucky. You can just kind of skip over details, be like, oh yeah, it's because it's similar to this algorithm. And you can't just say that, but that'll get you enough points, probably 7, 8 points. So let's see what happens in the code. Okay, include math, that's cool. Then we have this function, which is just calling this rec function, which is really what we care about, calling calling this function or this function right here. It's just dependent on whatever the runtime of this is. So now let's see what this function looks like. All right, so first things first, array. So some sort of elements. We have a low and a high. Okay, so that might help out a little bit. Now here we have an if low equals high, return array of low. Okay, so we're returning a value in this case. So this is actually a base case because it's kind of like being used, they call it like guard clauses. It's just one case, and after this case, you're going to want to do everything else. So this is really the base case right here. And we're just returning, whatever the number is at that index, which is really the same index. Then we have a call to the left. We have a call to the right, recursive call. But let's see what's happening. So we have low, that's going to be passed into the low parameter. And into the high parameter, we're going to pass in low plus high divided by 2. So normally when you're doing, some algorithm, you might want to calculate the midpoint by doing low plus high divided by 2. And you might have a variable that says mid. So right here, you can think of this as kind of a midpoint. So we're kind of splitting an array, at least for now, we're splitting into the left side and processing the left half where we currently are. Then we have the right where we're actually doing the opposite. Now that we split the left side and we've done stuff on the left side, now let's do it on the right side. So we are making recursive calls to one half of the array at the current call based on the current indexes, and then eventually to the other half of the array, since we ended up doing +1 and then going up to high. Okay, so I'm sure you guys probably have an idea of what the algorithm is, but now let's see what else we got. So we have a for loop that goes from low to high, inclusive, and we're just doing some sort of math. So we're just doing plus, 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 okay, based on whatever the conditions are in this math right here. And we have another base case where we're just going to change whatever value it is that we're returning, right? Now, the thing is, if we notice what this for loop is starting at and ending at, it's just dependent on whatever subsection of the indexes we are at. So you can think of it like kind of like subarray is the term we would use, but let's say we have an array 1, 2, 3. Let's use different numbers. 5, 4, 5, 4, 3, 2, 1. Okay, so we have these terms. We know that our indexes are going from 0 to 4. So we can think of the first call, we're going to have our array, and we're going to have 0 and 4. Eventually, we're going to end up going 0 to 2. Then we're going to have another call to 0 to 1. And when they're equal to each other, we're actually not there yet. 0, 0. This is the base case we're returning right here, right? So now we're going to have to process this other half. So we've done one half, we've just processed one. And now we're going to go into the other half. So that's going to look like a of 1, 1. Okay, so that's good. And now we're going to do the for loop. We're just going from 0 to 1. So that's one part and one subarray that we're dealing with. And now when we come back up here, now we're going to have to process this other side. And what that's going to look like is we have 1, 2, 1. Actually, sorry, 2 to 2. That's the other side. And then we're done. We do our for loop from 0 to 2, and then we keep going. So what type of function or what kind of algorithm that may or may not have been used in CS1 does that look like? It looks like merge sort, because we're splitting the array into different halves. We're only doing it once, right? We're always splitting it up into left half and right half. And then we're doing some sort of for loop. Now, the thing is, normally when you code merge sort, when you're in CS1, you don't end up normally you don't think of doing it within the actual merge sort call, like where you're going to be merging. You don't typically merge, or you don't iterate inside of the merge sort call. You typically call a merge function, which ends up going exactly from low to high. In this case, it's just doing some sort of math and then just returning those math values. So these values do not influence what the bounds of this function, or sorry, of this for loop are going to be like. It's not dependent on what you return from left and right. So that is something to think about. So we're just doing a for loop over the same thing that merge would go over. So we can just assume that we're going to have a runtime of n log n. We're splitting it up into halves and so on, and then we're also doing for loop for every single one of those like subarrays that we can go through. So for this one, it's n log n. And let's see, we also need to have proofs, determine the big O runtime. And you can end up kind of breaking down what I said and putting that into your proof. I'm not gonna write a paragraph now, but that's pretty much it. So you just kind of explain the thought process of how it works, and takes n divided by 2 time. There's a for loop, and it goes through at most n elements, and so on. You can, oh yeah, I also forgot to write this out, but this is actually what it looks like. So like I mentioned, a recursive call to the left, a recursive call to the right half, and then you're also iterating over that subarray. So this is really what the recurrence relation ends up looking like. And if you solve this out, you would end up with this. This is actually one of those recurrence relation questions that comes up sometimes. But yeah, that's pretty much it for this question. Remember to write out the recurrence, because I actually forgot to do that. So for proofs, we write a paragraph and calculate the runtime unless it's specified otherwise. Yeah, that's pretty much what I've seen. That's pretty much what I've seen for the most part. It's like there's some of them where, like I said, it's not okay. It's quick, so it looks like quick sort, or it looks like merge sort, or it looks like binary search. Like, of course, if it says that, then you can do that. But if not, try to kind of just think about it. Okay, if they say we can't explain or we can't reference, for example, binary search, since it might be a different application of binary search, you can just say, okay, so it's dividing the array into parts that are half the size than it previously was, and so on. So we can model this behavior. Let's say we started off with 8 elements, then we went to 2, then we went to 4, then to 1. If we take the log of the number, so for example, if we had let me just write this out real quick. So for example, if we had n equals 8, right, and we're going to do a binary search on these elements, we can think of it like this. So we know that at the start, we're going to have a window of 8 elements. So now we have 8 elements. Then we're going to choose one half to go down. So now let's say we choose the left half. So now we're going to have from 0 to 3. Now we're looking at 4 elements, right? So we can just kind of ignore this right here. Then we're going to choose a side. Let's say we choose the right side. Now we're going to go from 2 to 3. So now we're looking at this area right here, which is just 2 elements. Let's say you keep going. You choose, let's say the left half to go to. Now you're looking at just 1 element. And then, here you can kind of stop, but this is going to be your base case. or actually 0 would be your base case, or if you just find it here. So you're always going to come up until 1, or in the case that the element isn't in the like sort of array that you're searching for, you're going to end up like crossing over your left and your like your low and your high and whatever. So we can just think of that kind of like 0, right? So we can see what the trend is right here. You can explain that we end up doing 1, 2, 3, 4, and you can think of it as 4 plus 1. But if we end up taking like the log of 8, log base 2 of 8 plus 1, this is going to be roughly equal to the number of calls we're going to do. So we can say that the algorithm is log of n, right? So without, and I haven't really kind of said binary search, I'm just saying like this is how the algorithm is moving. You can say, you might be able to say it's similar to binary search, but by using stuff like this and this type of thought process, you can communicate the same thing without actually saying, binary search right then and there. But yeah, again, dependent if they give you the note or not. But yeah, well, I'm gonna wrap it up there. I think we covered like pretty much most of the type of problems that come up with algorithm analysis. Does anyone have any other questions? It can be recurrence relation, summation, base conversion, or algorithm analysis. Iterations, sure. I can do one real quick. Okay, I don't think I did this one. Oh, actually, this one we're gonna focus more on like these numbers right here, but let's go to a simpler one so you can see how that'll work. Okay, this is probably the weirdest one. Okay, I already did this one. All right, I think, yeah, this one's simple. Let's do this one. So this is what we're dealing with. And so T of n equals 2 T of n over 2 plus 1. And we have our base case of T of 1 equals 1. Okay, so I'll just summarize it like this, step by step. Do your 3 iterations. Find out how this number and this number are changing. Or if it's like n minus 1, how this number is changing. And then figure out how this summation is being built, or how these numbers are being aggregated, and then put that in terms of a summation. So we're just going to substitute what the next recursive call will look like. So if we think about it, yeah, no problem, Colby. So again, if we think about it, it's going to be dividing this by 2 again, because every recursive call is the same. If for example, if we do factorial, we're going to start, let's say n equals 5 in the first call. We're going to go down to 4, 3, 2, 1, and that's where we're going to stop, right? So we're going to apply the same logic. So let's say our n in this problem is 64. In the next call, if we're dividing by 2, we're going to have, for example, 32, 16, 8, 4, then we're going to have 2, 1, and so on, right? That's about it. So that's kind of the thought process of why it is now we're going to do n, or sorry, 2 times 2 T of n over 4. Because yeah, so initially you pass in 64, which is your n, but in the next call it's going to be 32, and in the call after this one it's going to be divided by 4 of n. If we passed in 64 as n initially, 64 divided by 4 is 16. So when we make this call, it's going to be 16 what we're passing in, which checks out with the math. And then, yeah, let's just keep going from there. This term typically is going to stay the same unless it's like based on n. And we're going to have a 1 on the outside. So now we just distribute plus distribute 2 plus 1. Okay, so now we can keep going. Let's do the same exact thing. Now we're gonna be at T of n divided by 8. So now we've got another level. Now we're gonna be here. Oh, 64 divided by 8 is gonna be 8. That checks out, right? So now we're gonna be plus one again. We're just gonna be following the same model. Then we still have these plus 2 and plus 1 on the outside. Distribute. Plus 4, plus 2, plus 1. Now we've done our 3 iterations, so that's about it. And again, identify how this number is changing. 2 to the 3, 2 to the 2, and 2 to the 1, all the way up here. So yeah, identify how this number is changing. Identify how the term that accompanies the n is changing. So again, it's following the same exact path with as this one right here. And of course, this one up here is going to be 2 to the 1. And then here, this goes 2 to the 0, 2 to the 1, 2 to the 2. Just find what the highest term is and think about how you can get to that term. If this is 3, this is 3, we can say that k is 3. And we can say if k is 3 here and this is 2, the upper bound of this summation must be k minus 1. And yeah, that's pretty much it. And then you can kind of end up solving from there. But that's pretty much how you can think of it. So identify the trend of these numbers, build out your summation, just identify it. What is it bounded by? From there, you're going to end up plugging in the base case, solving for the terms. You find like your general form and all that stuff, and then you just plug and chug with algebra. That's about it. Can you show the answer for this question at the end? Yeah, sure. Okay. So I'm gonna have to solve it then. I'll just do it quickly. You guys can just watch, I guess. Okay. Okay, so right here, we're gonna have our substitution, and we can substitute this with n. So we have n plus n minus 1, which is equal to 2n minus 1. All right, so let's see that real quick, and yeah, that's the answer. All right, so yeah, that's pretty much it for this. And by the way, I did want to mention to you guys, Eli, did you want to talk about the way we're gonna do next week? This is gonna be like a mock exam, guys. We're gonna be going over one of the foundation exams, probably the most recent one. And we can just kind of solve it together. It'll be a little bit longer than normal, if possible, because I think the idea is kind of like maybe do it along with us, or we might just try to solve it a little quicker than usual. So, we're not here for 3 hours. But yeah, that's the idea. Just go through a mock exam and any last minute questions. And that'll be it. You guys are gonna be taking your foundation exam. Yeah.
Yeah, any of those plans sound good to me. I know I'll be available until 10 p.m. Like if people need to stay after and ask some questions, that doesn't mean that you have to be available if if you're not.
Oh yeah,
But
I'll be available. It's cool.
we can, I can stick around a little bit after to answer any questions. I think if we, I know I don't want to like remove a question from each section because I feel like that isn't super helpful.
Right.
But we could definitely give people like do one question at a time and maybe give them like if each question is 10 minutes, give everyone like I don't know. I think we should talk about like how to do it afterwards. But I would say that everyone who's still here, like if you have the availability to block out until 10 p.m., do so. If you can't, then we'll try and get as much done before 9 as possible. And then we'll figure out the specifics offline before
Yeah.
next week.
Yeah, and again, the session is going to be recorded, and you can watch it later on between Thursday and hopefully not on Saturday, but you guys can just watch it during that time. And also again, there's other videos. So I had done one with Night Hacks, there's with Chef,